Welcome back, everybody, to Easy Astronomy. I wanted to go through this. I've actually spent quite a bit of time tonight working on this, and just wanted to kind of get it out there. I think when amateur astronomers talk about sky quality, and you're going to hear that, you're going to see it a lot in my posts. You're going to see it on a lot of the sketches that I'm going to post up for my observing sessions. They usually separate sky quality into two main things. One is seeing, and the other is transparency. And seeing, it really is how steady the atmosphere is. A good way to think about seeing is, I've said this before, is when you're swimming, if as a kid or even as an adult, if you go to the bottom of the pool, whatever, and you look up, and there's a lot of movement of the water above you, it kind of blurs everything above you. If the water is very still, you have a very clear image coming through there. That's how seeing works. And transparency is really how clear. It's not whether there's movement of the water, or in this case the air above us, it's how clean that air is. For example, you could be in water at the bottom of a pool and look up and the water could be absolutely still. But if it's very cloudy because of pollutants and other things that are there that are stirred up, then what's going to happen is you're not going to have as clear a view of that object as the sky would allow. You're going to find that usually in astronomy, transparency and seeing are the opposite. If transparency is excellent, seeing's usually not that great. If seeing's great, transparency is usually not very good. Okay? Seeing affects resolution, how sharp planets and double stars and fine lunar details, craters and contrast on the moon, how that looks. What good seeing versus bad seeing looks like. Good seeing, stars are going to look very steady at high magnification. There's not going to be a lot of scintillation where they're twinkling. Okay. Planetary, when you look at a planet, it's going to come into sharp focus. Back in November, Shane and I had just probably one of the best views of Jupiter I've ever had. Transparency was probably average that night. The seeing was excellent to outstanding. When we looked at Jupiter at the end of the night, you could see the little wisps coming off the bands. The red spot actually had not just the red spot, but dimension to it. I mean, contrast there. You can see some modeling. The modeling on the planet was beautiful. Probably one of the best views of the last probably 5 or 6 years I've seen of Jupiter. It was just so fantastic. When you have poor seeing, stars are going to twinkle very strongly, and planets are going to look like they're boiling or swimming. I had that last Thursday night out at Erickson Pass, the Corral site that I posted about. Seeing was good, was average. Toward the end of the night when I looked at Jupiter, which is the last object I'm going to look at, it was okay. I could see the bands and stuff, but the seeing just was average. It just meant the planet looked average. It didn't stick out. It just didn't pop. Okay. How to judge seeing at the telescope? Usually you do that with a star test. You find a bright star up near zenith, and you're going to use high magnification, 30 to 50 times per square inch of aperture. And so, for example, on my 17.5-inch Dob, if I'm really going to bring that high aperture in, I'm going to go up to about 600 to 800 in magnification power. If looking at that star, if it's constantly blurring into a fuzzy blob, that means poor seeing. Okay, if it's sharp and crisp, good seeing. The next test that you're going to do, and you can see it, I'm just going to go through it on here, just kind of going through the outline of what I've done here, and so it'll be on the Patreon site, so you can go through it. Is to do a planetary test. Jupiter, Saturn, usually the best, like I was just saying. When I looked at Jupiter in Lakeside in November, I could see those fine belts. The festons really stood out, and the ring structure on Saturn, I've seen it where you can really see the Cassini and the secondary division line in the rings, and they just really pop out. If details appear only in brief flashes, like that's what was happening last Thursday. I'd look, it would just come into really good focus for just a moment, and then it would boil again. That's average. That's average seeing. I've had it to where when I've looked at Jupiter or Saturn, especially Jupiter, it's never sharp. It's more of a blur image. That's when you know seeing's poor. There's a couple scales to use with this that people have come up with. One is the Pickering scale. It's set up to where 1 to 3 is very poor. You can see it's boiling. Stars are boiling. 4 to 5 is average, like I talked about. 6 to 7 is good. Not so much boiling. You'll get moments on the 4 to 5. You'll get moments of steadiness. 6 to 7, you're going to have just minor scintillation on stars. You're going to have the planet looking good most of the time. Fades off every once in a while. 8 to 10 is excellent. Those are rare nights. It means that it's focused and stays in focus, like that night I had in Lakeside in November. I have put a link on the page for examples of that. I actually included one here. You can see 1 through 3, the star is very boiling here. 4, 5, that's an average look, kind of comes and goes. 6, 7's good. It's probably more of the type of seeing conditions we're going to see. If you get these, especially that 10, that's a night of nights, as I call them. You can go through that. Just talks about it. The thing with Pickering is he came up with the scale using a 5-inch refractor. So you kind of have to modify that a little bit if you're looking through it with a bigger telescope. The other scale is the Antonati scale. You'll see that on my sketches. It's just designed for a quick hit. I'm putting the scene in transparency as I measure it on the sketch itself. The Antonati scale starts numeral 1 through Roman numeral 5. 1 is perfect seeing. There's not a quiver in the star. 2, there's maybe a slight quivering with moments of calm that last for several seconds when you're looking at a star. And this could be visual or through the scope. A lot of times I gauge it off my visual observation. 3 would be a moderate seeing. There's large air tremors that are going to blur the image. 4, poor seeing, constant troublesome undulation of the star, of the image. And 5 is very bad. It's hardly stable enough to really even to consider making a sketch or even to observe. If it's really bad, you kind of pack up and call it a night. Transparency, atmospheric clarity, that affects brightness and contrast, and it's really critical in deep sky objects. When you're looking at a galaxy or nebula, you really want to see the contrast that's there. What hurts transparency, you can see here, thin, high cirrus clouds will impact it. Haze, smoke, dust that's come up into the air, that's settled in the wintertime here in northern Utah. We get inversion in the valleys where the cold air is trapped. It's warmer up above. That cold air traps pollutants and it usually spreads, and that will impact transparency. High humidity, I don't have to really worry about that in Utah. Light pollution combined with that haze. I can really tell when I have a poor transparency or an average to poor transparency night. When I'm looking to either the northeast or the east or to the southeast, depending on which observing spot I'm at, that I'm going to, and I can see that instead of 20 degrees up, 2/5 above the mountains, that light pollution dome has increased to 30 or to 40. There's pollutants in the air that are allowing the light to scatter and increasing that light and actually causing the sky to be brighter than it really is or should be typically. And then a couple of ways that you can judge transparency. One way that people talk about is naked eye limiting magnitude. I have some problems with this. Part of the problems is my eyes at 60 are not as good as my friend Shane's at 45, 46 that he is. His are a little sharper. I have more experience, so I can see more things, I think. And I still have pretty good eyes, to be honest with you. My ophthalmologist a couple months ago was amazed at my age, how good my eyes are. So that was a good thing. But anyway, and also there's just a lot of factors that play into it. You got to be able to know the conditions that you're looking at, gauge those conditions, and then gauge what your experience and what your eyes based on your age are. And so it really could come down to, I say it's one thing if I'm using naked eye limiting magnitude. Shane could go a little deeper with younger eyes and more experience. It just really just depends. But anyway, under limiting naked eye limiting magnitude, you're going to look at a familiar constellation, usually star field. Ursa Minor is one, Cygnus is another one that's commonly used, and you're going to see stars down to a certain magnitude. You're going to see visually how many stars you can count. There's usually a chart, and on those charts you can see exactly what magnitude you're seeing naked eye. So if you can see down stars that are only in the magnitude of 4 to 4.5, that's a poor transparency night. If you're going to magnitude 5 to 5.5, that's an average suburban transparency. 6 to 6.5, that usually means that you're at a good dark site. If you're seeing anything above mag 7, that's an exceptional sight. And you can see that I've printed, there'll be apps and charts down below that you can print to get that. The Milky Way visibility is another way to gauge transparency. If it's invisible, washed out, not a lot of detail, usually poor transparency. If it's visible but faint, average transparency. If it's bright, structured with dark lanes, you can really see the dark lanes in it. Usually a night of excellent transparency with that. I do use the Milky Way visibility to kind of gauge transparency myself. You can do a telescope test with deep sky objects. This is another way that I do a lot of this. You can take a faint object, galaxy or nebula. If it looks dimmed or washed out or disappears with slight haze, poor transparency. If you see contrast with it, faint extensions, faint detail in it, usually you have to have good or above average transparency to see that kind of detail. So here's just a common chart that came together for this. If you see sharp planets but faint galaxies are really hard, you can basically know that you have good seeing but poor transparency. If you have blurry planets but faint galaxies are really bright with some detail, that means poor seeing, good transparency. If you have a great deep sky night but it's horrible on the planets, your seeing is poor, your transparency is excellent. I've had a couple of those recently. And then you have a great planetary night, but a weak Milky Way, that's excellent seeing, poor transparency. And you could play around with that, and we could put some other things in there just to kind of show it. You could have a great planetary night and great deep sky night. That would be like the ultimate, and I maybe had that twice in 25 years. Some practical tips at the telescope. Check seeing first before cranking up magnification. If your seeing sucks, you may try to go high magnification. All you're going to do is blur out your object. You're not going to see details on it. If seeing is poor, switch to wide field observing. Open clusters are great for that. Good deep sky objects that are pretty wide field are good for that. If transparency is poor, focus on the moon, planets, double stars. Those type of things, kind of leave the deep sky alone. There's some weather clues that you can look at. If you're here in northern Utah or anywhere on the west coast or even in the east coast, if that jet stream has dropped and is right on top of you, that's a good sign that you're going to have bad seeing, because there's so much turbulence up there in the atmosphere with the air moving, just makes for bad seeing. If you have calm high pressure systems, those usually lead to good seeing, but then as that haze and stuff builds up, bad transparency. If a cold front has just passed within a day or two, my experience is, especially here in Utah, that probably not the day right after a storm, the second and the third day, those can be the nights that I want to get out if it's clear, because those are magical nights. I'll still get out the night after if it's clear, but I kind of tailor what I'm observing for, and we'll talk about that in a few minutes. Okay, so it looks like some of my links that I had put in here didn't come through. I'll have to go back and put those links in there so you can find the finder charts. So how do I determine seeing with my 17.5-inch Dob? And this is probably good for anywhere from a 10-12-inch Dob up to about 18-20-inch Dob. I choose the second or third magnitude star near zenith, and I'm going to use 300 to 400x. You can see here I've listed what eyepieces those are. It's usually going to be 7mm Pentax or 7mm XWA, down to the 5mm Pentax XW or the 4.8 XWA. And then I also use my classic 6mm beta ortho classic or my University HD ortho 6mm. Usually the beta, it's a little bit wider field of view than the University. And then I bring it to exact focus. If I can see as I bring the object, the star, to focus, that it's tiny, stable with just a slight airy disk, maybe the first diffraction ring is mostly visible, I know I have excellent seeing. Good seeing is the disk is visible but dancing slightly a little bit. Average, the star swells and shrinks, there's no clean disk. And more often than not here in Utah, I'm probably going to see that just because we usually get that jet stream coming around. Poor star looks like a shimmering blob when I focus it. With my 17.5, if 350 magnification is usable, it's probably good seeing. If 400 will hold very occasionally and I get some good spots in that, probably very good seeing. If I can go up to 600 or greater and it's stable, that is an outstanding seeing night for me. It's exceptional. I can use the galaxy nucleus test for deep sky specific objects. I can pick a compact galaxy M82, NGC 7331, Messier 104. If the core is sharp and steady, the seeing is good. If the core smears or pulses, seeing is limiting me that night. Here's something really important, is to give a thermal reality check. Before blaming seeing, though, and just saying, no, this sucks because the seeing just sucks, check your thermals, okay? Let the mirror cool at least 60 to 90 minutes before you observe. If at all possible, use your rear fan continuously at low speed during the night. It will keep that mirror approaching or at near equilibrium. If you don't, it can become, as the temperature drops, that mirror is still shedding heat, and so you're going to get some turbulence there, and that's going to affect the seeing. Okay, again. Turn off fans briefly to see if a star image improves, and if it does, then you know you're probably pretty good to go. Poor thermal control mimics bad seeing in big daubs. Remember that. If you're using a daub and you're having that, but you have bad thermals, it's going to imitate bad seeing. You could have actually great seeing, but if you have bad thermals and you haven't cooled your mirror properly, you're going to have a distorted image. Okay? Here's some things: fan usage and thermal strategy. It's critical for Utah or the deserts area. Large mirrors absolutely require active thermal control in Utah's temperature ranges, or anywhere where you're having an extreme temperature range in the desert. The deserts of Southern California, the deserts of Nevada, Arizona, New Mexico, Oregon, in the eastern part of Oregon and Washington. You're going to want to start fans immediately when you set up. If the temperature is dropping greater than 10 degrees, which is common in Utah and common in the desert areas, you're going to run your fans at full power for 35 to 45 minutes. During observing, drop those fans to a low continuous speed, and continuous airflow is better than cycling. That's why a lot of times I'll leave my fan going. Fan configuration, these are ideals. Have a rear fan for the primary, always on at low speed. Its purpose is to remove the boundary layer and help to equalize the mirror. If you can have side fans blowing across the face of the mirror on the top, use them for the first 30 to 60 minutes to kind of get those thermals off that mirror as it's coming off, and turn off to reduce once your star image is stabilized. You can check while you're observing. You can go to 300 magnification power, turn your fans off briefly. If a star gets worse, you know you need your fan back on. If the stars improve, it's reducing vibration or airflow, and you are pretty good to know you can probably go without your fan. Your boundary layer test, which is very important here, defocus a star slightly. If one side of the disk looks smeared, you still have a boundary layer present. Fans will fix this better than just leaving it and letting time alone try to equalize it out. Some specifics for desert areas, Utah thermal tips for those observing in desert locations in the west. Here's the reality with a high desert area. You have rapid post-sunset cooling. Temperature is going to drop. It could be 100 degrees. I could be going down to 45 degrees. That's a 60-degree span 55, 60-degree span that I could be losing. That means that my mirror is probably going to always lag a little bit behind. Expect 2 thermal transitions at night, from sunset to midnight, and then from midnight to dawn. That transition from sunset to midnight is going to be fast. That's when the temperature is going to drop the fastest. From midnight to dawn, temperature tends to stabilize. The mirror will begin to stabilize a little bit more. It's especially important in the summer, I feel. So that's another reason to keep your fans running all night. The winter, cooling is easier than warming. You start your fans early. That's why you should get out to your observing site, if at all possible, a little early and get set up so the fans can do their work. And then you can turn them, never turn them off, because the temperature continues to drop in the winter. Your mirror is still shedding heat, so you want that fan to help eliminate some of those boundary layers that are coming off. Mirror equilibrium, best galaxy detail window. When that mirror can be really close to the outside ambient temperature, and they can be very close, that's the best time for galaxy viewing and getting details out of your galaxies and deep sky objects. How to determine transparency at a dark site here in Utah or at a desert location. Some will use the limiting magnitude to determine transparency. We've talked about that. For me, I really feel that's hard because, like I said before, it's really based on the observer. Younger eyes are better, older eyes have more experience, okay? Which also helps. The location can vary. You could be down in a valley, like at the bottom of a bowl, instead of up on a ridge or a hill, and that could impact what you're actually seeing and the conditions that you're in. However, my main way, and I italicize this, of determining is, as I look at objects, planets and deep sky objects per above, I look at those more to determine what my seeing and my transparency are. I use the actual objects to help me to determine that. And so it really comes down to, I think a lot of this will vary a little bit from observer to observer. And I think that's okay. It's when you're observing with somebody else that you guys can have those discussions, and you can probably come to a conclusion with each other's experience on what the actual conditions are. It's another reason to go out with somebody. You can use Cygnus or Sagittarius seasonally to kind of gauge naked eye limited magnitude. 6 to 6.3 stars that you're seeing there are decent. Probably a little bit of haze. 6.5 to 6.8 magnitude, limiting magnitude on stars that you're seeing in those constellations. Probably a good transparency night. If you're a 7 or above, that is exceptionally. That means it's a great dark site, and it's an exceptionally clear night and a wonderful night to go. If you can see Milky Way casting shadows or show dark lanes, that means you have top tier transparency as well. The following links will provide some of those naked eye charts I thought that I'd left out up there. They're right here. You can see this link will take you to a PDF of naked eye limiting magnitude charts that are by constellation, and if you want to give this a method a try, link 2 goes to a star chart for globe at night 2025. He should have 2026 coming up, as he mentions on his site. Sometimes he forgets to update the year. Link 3, magnitude charts for the constellation Perseus at 40 degrees north. Segura Astronomy, determining the limiting magnitude. You can see charts and stuff at that link. And then there's a couple here from the Arkansas Sky Observatory for limiting magnitude. Sorry, I don't know why I got this little cough. Determining using Messier 45, the Pleiades, or the Hyades and Taurus. And then they also have one for winter skies that are there. I prefer to do the following myself. I prefer to do a low power galaxy test. I insert my wide field eyepiece, likely somewhere between a 20 and a 32. I look at M33, NGC 6946, and IC 342. If they are hard to detect, especially M33, if I'm looking at M33 and it's really hard for me, I almost have to have averted vision just to see the fuzziness of it, that means my transparency is poor. If it's visible but very faint, very weak, not seeing tons of structure, probably have average transparency. If it looked like it did last Friday night, where it just popped, and with averted vision I could see the arms and then hold them with direct vision, excellent transparency that night. 17.5 inch Dob, or anywhere in that 12 to 18 inch, 12 to 20 inch should show spiral hints in M33 on a truly transparent night. Like I told you, I had that last Friday, December 12th at Erickson Pass. Talk about that there if you want to read that. I've also had times where the sky looks great as I'm going out. I think it's going to be a fantastic night. But then when I look east and north, when I look at that light dome going from Ogden to Salt Lake, or Salt Lake to Provo, or Provo down to Spanish Fork here, when I'm looking east, northeast, east, southeast, depending on the observing site, and I see that light dome is above 30 degrees, I know that conditions have changed. I've gotten some haze, I've gotten some jet stream or something that's blown in, and the transparency has fallen off. If it stays under 20 degrees, I know I'm having probably a pretty decent transparency night, if not an excellent one. You can read about that. I basically say, otherwise there's particles in the atmosphere. That's really what they're doing. Those particles will scatter light from the light dome, and that impacts both transparency and the darkness. I get brighter skies, I get worse transparency, and when I take the measurement with my SQML, my sights actually decreased several tenths from what typically is. I posted some pictures on the site. You can see here, this was the drive out last Friday. This is an example of outstanding transparency. I knew I was going to have a good night if the conditions held, just by the details I could see, both in the road, in the grasses, and the mountains ahead. Okay. Another way that you could do this is globular halo reach. You can observe Messier 13 or Messier 92. If the stars resolve well into the outer halo, you got a good night of good transparency. If the halos look washed out, transparency is limiting that contrast. You know it's not that great. Quick at the scope decision guide. This is meant as a guide if you use a 12 to 18 or 20 inch daub on what target based on conditions. I don't share this much, but this is basically my basic guide. If transparency is excellent, but seeing is mediocre or average, I'm going to focus on galaxy clusters, Coma and Virgo, large nebula with filters, globular clusters, and low surface brightness galaxies. Just because the transparency is going to show more detail, more contrast, I'm going to avoid the objects that I need good seeing for. However, if seeing is excellent but transparency is only average, I will look at planetary nebula at high power with that. Small galaxies with bright cores are good for that. Tight galaxy groups are also good. And fine structure and globular cores are really good for that. If both are excellent, those are the nights of nights. Those are the once or twice it happens every couple of years, maybe if you're lucky. That's when you want to go for able galaxy clusters. Higgs and compact groups are good that night. Faint IFM and galaxy tidal streams. On the mice, that's when I've seen the tails on just nights of when they both are just been outstanding. That will explain some nights, even though I may tell you that I'm going to be going after able galaxy clusters or able planetary nebula or Higgs groups. I don't go. I get out there and the conditions are such. I evaluate the conditions in my mind and I make the decision that night I'm not going to waste my time chasing something that's just going to be too faint and not give me the satisfaction that I'm looking for, or the challenge really to see how much detail I can get out of them. Comes back to this. Know your local weather, know your regional weather, know your observing sites, and how regional and local weather, regional impacts local weather, which impacts that observing site. That will help you to guide how well the transparency and the seeing are going to be there that night. Know the objects you're going to go after. I don't put that in here, but if you know you're going to go after objects that need excellent or above average transparency, then you want to make sure that you're picking a site that's probably going to give you that. If you're going to be going after items that need great seeing, then you're going to want to be in a position where you pick one of the observing sites where those conditions are. So all things to take into consideration when you're picking a site to go observe. Here's some specific clues here in Utah or in desert areas of the West. Post-cold front winter nights. I've talked about this briefly. I'm going to get more into it. Transparency, that second and third night after a post-cold front has come through, is probably the best I ever get during the year. Seeing may be mediocre early, and that improves after midnight, or it improves after that cold front has transitioned out and the high has stabilized that night, before pollutants can get trapped in the valleys and you get inversion and other haze and smog and stuff building up. Those are the nights of nights. That's when you want to go, as I say here. You'll find those nights are fantastic. I usually get a couple a year if I'm lucky, and that's why I usually always go out in the winter. It's probably some of the best time for transparency and seeing that I've ever had. Late summer, monsoon moisture, seeing can be good. Transparency is usually pretty poor during that time. And that kind of is a time where I'm going to go after more open clusters, globular clusters, bright planetaries, things like that. Fall, spring nights, usually I get more calm, high pressure nights in those times. That's the best balance of both. That's why I prefer fall first, spring second, winter third, summer last. Just because I'm a deep sky fanatic, but I've learned to adjust. I truly like those nights where I have it at home when the moon's up and I just have outstanding seeing. I can really get good contrast and good sketching and images from the moon. So if the Wasatch or the local mountain range is sharply silhouetted at sunset, you can probably know that transparency is excellent. I'll use the images below to kind of show you what this means. This is from right here the other night, out on Friday night, December 12th, Erickson Pass. Great transparency here as the sun was setting. This is Lakeside. This is probably average to just slightly below average transparency. It's there. I'm not seeing a lot of detail on those mountain ranges as I'm looking there. They're kind of blurry to me. Average transparency, and that's what it was that night. This was Horsehead Knoll looking west. This is definitely below average. See the haze that's down there. I can see the haze in the atmosphere. Definitely see the haze along the mountaintops. That means that I'm going to have that. This is one of those nights to where if I was facing eastbound, instead of having the light pollution from the Salt Lake area right about here, it's probably going to come up to here. That means it's going to scatter up even higher, make my sight brighter, make my transparency poorer. All just what objects I'm going to go after when I see conditions like that. Doesn't mean that I don't go out. I'm still going to go out and observe. It's just going to tailor what I'm going after. Here's the Stanberry Mountains in Skull Valley. This is very good transparency. I can see little detail on the juniper here. I can see details in the mountain ranges up here. See some crevices and shadows up here. Very good transparency. Here's an example of excellent transparency out at 8 Mile Spring Road. I can see detail in the distance here. I can see the details in the sagebrush out there. Good distance off. The mountains were clear and sharp. Excellent transparency that night. This is when I went to the Knolls in November, late October, November. You can see that night. Look at the detail on that hillside over here. About a half mile away. Just look at that as I zoomed in. It held the zoom. It was just clear. Looks a little hazy. Really wasn't. A little bit of haze down low, but it really didn't impact up. And the transparency was just gorgeous. Here's another view from the same location. I could see really far in the distance. I could see details. See the details on there. Just how crisp and clear it was. There was some dust up in the atmosphere. You could see that hanging in. That limited the transparency, but overall, I would say it was very good to excellent. These are just some examples that you can use and look at. So here's your 1 minute test routine. Defocus a star at 350 magnification for a seeing check. Use M32 or IC342 or M33 at low power for a transparency check. If it's faint or just a blur, transparency poor. If you're seeing good detail in those galaxies, you have good transparency. And then you can decide on what targets you're going to go after accordingly. So I have multiple lists and I work from multiple lists. I tailor my list based upon the conditions that I'm in right now. I'm going to move on to the last thing here, optimal exit pupils for my 17.5-inch Dob. I have one of these. I don't know. Nope, I cut it off for the 14, the 10, and my refractors. I have the field of view degrees, the magnification, the exit pupils here, And then if I'm using the paracord 2, the impact of the paracord 2, and whether it's considered very low power or high power or very high power. You can see that there. The keys here are the exit pupils, both with and without the paracord. They're in that kind of golden yellow color. You're going to want to use that. Remember, exit pupil equals brightness plus contrast. In large knobs, the most faint details live between 1.3 and 3.5 millimeters of eye relief. Use bigger pupils for detection, smaller for structure and details in your deep sky objects. Exit pupil ranges, what to use them for. If your exit pupil is between 5 and 6.5 or greater, that's probably going to be low power mode. Let's find an example of that. Right up here, I have the Teleview 35 millimeter panoptic. With the paracord, comes in at 7. Without the paracord, it's at 8.05. Definitely going to be a wide field, low magnification eyepiece. Oh, sorry, long day. Anyway, you're going to use that for initial object detection. Integrated flux nebulas are great for that. Very large nebula like the North American, the California. You also can use it for star hopping. A lot of people will take an eyepiece like that and actually use it instead of a finder scope to save the weight and the balance issues on their scope. And that's how they star hop. I've done that. It works very effectively. If your eye only opens to 6 millimeters, though, or less, anything above the diameter of your pupil, then you're wasting light, and you just need to realize that. Sky background here should always look black and good at a desert site or here in Utah. 3.5 to 4.5 millimeter eye relief. That's a low power. I call that low, the higher end of low power or medium power. Magnification is going to come in at between 100 and 300, 130 magnification. Eyepiece range here 20 to 26. You're going to use this for large galaxies like M33, M101, and GC 2403. Galaxy clusters like the Virgo or Coma, where you want to see as many as possible. Large emission nebula with filters on them. It's really good for that. It's the best balance of brightness and contrast on dark nights. If you're going to go down to those eyepieces that have 2.2 to 3.0 millimeter of high relief, those magnifications are going to be 150 to 220, 230, somewhere in there. Those are probably your 13 to 18 millimeter eyepieces. Those are good really for most galaxies, globular clusters, structure nebula, dust lanes, spiral hints. If you only had one exit pupil and an eyepiece to use, this would probably be the eyepiece that most people would pick. You're not going to see tons of extra detail, but it's going to look pretty decent. I know that if the transparency is average, a lot of times instead of going down to the 9 or 7 millimeter XWA or the 10 or 7 millimeter Pentax XW, I'll usually put the 13 millimeter XWA in and use that. The 20 becomes the finder, the 22 Nagler does. If your eye relief is getting down to 1.3 to 1.8, that's high power, and that's going to be used for galaxy cores and knots in the galaxy arms, planetary nebula to see dual structure, inner and outer shells, resolving globular cores and getting more of the stars in the cores out, and tight galaxy groups like the Higsons. That's going to require decent seeing and good thermal equilibrium on your scope, and probably decent transparency. High power, really high power, magnification 400 to 600. You're going to use that for small planetary nebulas, central stars, and these are for those exceptional nights of seeing. You put a planet in there on a night where it will take this magnification, it is stunning. It will blow you away. If the object's harder to detect in a exit pupil eyepiece, then go larger. Go up in size. If my 7's too blurry, I go to the 9. If the 9's too blurry, I go to the 13. Okay, be willing to make those jumps. You can also continue to do that. You go from a 20 to a 13, try the 9 and see if the 9's good, see what the 7 is. Anyway, just something to keep in mind. If the object is detected but flat, go smaller. If there's detail flashing in and out, probably your seeing's limited. Some basic rule of thumbs. If the image improves slowly over an hour as you're looking at it, that means your mirror is continuing to cool. If the image improves instantly when the fans are on, you know you have a boundary layer issue. If the image never stabilizes at any power, you're just facing a night of poor seeing or really poor thermals within your scope. Usually poor seeing at that point, especially if your mirror is cooling. If the galaxies lack contrast at all powers, all magnifications, poor transparency. It pertains to Utah, but it's good for anyone in the western United States or in dry climates. The perfect night setup routine. Set up before sunset. Try to get out there. I talk to Shane about that all the time. Run your fans at full power at dusk. Get your scope set up before you do anything else and get the fans running. Put them on low power after 45 minutes after sunset. The first serious observing, try to use your 2.5 to 3 millimeter eye relief range. Push to 1.5 after about 11 o'clock midnight. Be a little earlier in the winter season when it gets dark a little earlier. Run the back fan on all night on low mode to keep that mirror cooling and equilibrium there. I've actually covered quite a bit tonight. This is probably a topic that's very dear and near to my heart. It's, I feel, one of the things that's probably least understood by most people in the hobby, except for those who have been around for a long time, but it's probably the most impactful. Once you understand this and how weather contributes to this and what eyepieces use and what objects to go after, that's when observing becomes fun. Observing becomes frustrating when you never ever get into this and never evaluate it. And I think that's why a lot of people drop out of the hobby. I like the challenge. I like learning. I like being able to put the pieces together, so to speak. I get a lot of satisfaction out of that. I hope you found this useful. I hope you found it helpful. If you have comments, feel free to reach out. I'd love to engage in a conversation about this. May your skies be clear. May your personal skies be clear. May you always look up and reach and have connections, both with the universe above and with each other. Have a great night.